That would have been a bad fail.
Really?
The last talk of the conference is going to be non-interactive key exchange in a generic multilinear group.
Cool. So I'm Valerio, and this is an old result, I guess, or kind of, yeah, that I've worked on with Allison and Luke. This was back in, I think, 2014 and 15?
2015.
Yeah. I remember the last time we failed this was 2015.
It would have been that we were trying to submit to TCC 2015.
Yeah.
That did not happen.
Yeah. I think we were in Berkeley as well.
Yes.
Cool. Cool. So, yeah, non-interactive key exchange. So what is it? It's, well, I copy-pasted it from a famous paper, so it must be this, right? So two parties who know each other's public keys want to agree on a shared key without any interaction. And of course, you can extend it to many parties with a ledger. Okay. So an example is the Diffie Hellman. So Alice samples a secret key, publishes a public key G to the A. Bob does the same for another variable B. And the exchange is the usual. I exponentiate by your public key with my own secret. And since multiplication is commutative, you get that, you get correctness. And security is, Diffie-Hellman. Cool. Okay, so can you extend this to many parties? Well, yes, you can. And if you want to keep it non-interactive, you could do it easily with n-1 linear map. So it's kind of the same. Each party samples their own secret, they publish their own public key, and so if I want to get the overall key, shared key, I'll just pair all the public keys that don't belong to me. I could do that because I have an n-1 linear map, and then use my own secret to exponentiate. Does that make sense? Cool. And security is just a generalized version of Diffie-Hellman. Cool. So do we really need that map though? Because n linear maps are maybe difficult or hard to achieve. I don't know. Yeah. So that's kind of the starting point of our paper. And so we showed that actually you really need n-1 linearity if n is small. So that's so if you think about the result like this, so each party samples uniform secrets. They only publish group elements, and it's a generic group, and the linearity is polylog, then we didn't fail. It's yeah. So that's kind of what I was mentioning earlier. Like all those restrictions apply because, well, we tried before without them and failed. And okay, so I'll talk a little bit about how did this whole thing happen. And yeah, this is kind of a message that I wanted to give you guys. Fail better, meaning different things. But mostly, don't be discouraged by failures. There are ways you can interpret them better, repackage them as results, and so on. Or, but I think the overall feeling is, okay, don't be discouraged by failure. It can happen. It's okay. Cool. So I think Yeah.
Waiting for somebody.
Yeah. It's also, there was this Buddhist nun who took this as a motto and gave a lot of interesting talks. So if you want to check it out, that's another thing. I think she said, fail again, feel better. Anyway, this is kind of my recollection of how we failed. 2014, we were here. I think you asked me, what do you think about this? Yeah, sure. And then in Berkeley, we failed again, and hopefully this is the time we feel better. But, maybe next time. Anyway, so I kind of want to show you a little bit about how the crypto climate was at that time, in 2014 and 15. And this, asterisk, this is my personal view. People can disagree. But the way I saw it was, we got multilinear maps in 2013. It's an exciting result, and it gave birth to all these papers that came out, and I think I call them like whatever from obfuscation of multilinear maps. And I mean, they essentially showed that you could do anything with these things. So I think at that point it was, probably what we were thinking, like, what can't you do with these things? And, one of the things we were thinking was, like, what about obfuscation for a small class of circuits or functions? Can you do it without them? And another angle is this paper. So, do we really need that level of multilinearity for non-interactive key exchange? So, that's kind of the motivation of the whole result. We want to really show that, yeah, you really need all the linearity that you can think. Okay. So, I'll show you why we failed a little bit, but kind of, we'll see later. So, if you don't have any restriction, well, I can just sample my own non-interactive key exchange protocol and forget about the group and linearity and so on and so forth. So I can do it with k-2 linear map. So yeah, that's not good for our result. So you have to make a restriction in terms of the published elements. So, okay, let's say that you're only allowed to publish group elements. Well, you can still kind of encode arbitrary information by adding correlations in your secret values. So as soon as you can convey a bit of information, well, you could kind of do the same attack as before. It's still, a failure. That's why it's the second failure, so 2 emojis there. And then, okay, so what if you have all restrictions except for the polylog? Well, I'd be very happy to hear that it's possible, but we didn't manage to show that there is a lower bound in that case. So essentially, we tried, saw that we really needed a polylog with that proof that we were thinking about. And I'm going to try to go through the proof in one specific case so that you kind of get to see the way we were thinking about it. Okay. Does it all make sense so far? Okay. Cool. So the proof is split into 2 parts. We're kind of doing, I wouldn't say the obvious, but the intuitive. So have an attacker, everybody has their k-2 linear map, and the attacker is trying to use this map to break the scheme. And yeah, the proof is split into two parts. The first part we show that whatever shared key that the honest parties can agree upon is belonging to a limited class of possible shared keys. Namely, if you can represent this shared key as group generator to the F, well, F must be a polynomial of bounded degree in the random variables that the players uniformly sample. And once we have that in place, well, the next step is to show that that class is something that any attacker can compute. So these two facts combined really show that no correct scheme is secure with all those restrictions and so on. Yeah. Cool. Okay, so the first part is really showing that these polynomials have low degree. So I'll try to do some more low-level details and hope that everybody follows. We'll see. So Alice and Bob have these shared key, and let's say that Alice writes it down as G to the A and Bob as G to the B. Can I erase the board?
Yeah, I already took a picture of it.
Okay.
Although maybe you should write erasing the failures as the last failure. It's
Well,
okay, go ahead.
It's one of those, it's not a failure. Okay. So, I think what I'm trying to say here is that Alice has G to the A. Is this good enough?
Yep, I'm just gonna zoom in a little bit.
Bob has G to the B, and these should be equal because it's a shared key. But A and B don't necessarily need to be equal as polynomials because, you know, what if there is different representation of a field element in the random variables? So that's kind of the tough part. So what about A and B? So we want to show that they have this low degree property. Okay, so we can decompose them as sums. I'll do a, so the way I'm writing it down is as a sum, and then monomials in, these are variables that are not Alice's, and then times a polynomial, and this is Alice's variables.
Question. That first part, is that from a trusted third party or something?
Say
The
again?
variables you're talking about?
So we have n players, so
Oh.
everybody is to the,
Contribute.
yeah, the contribution from everybody else, because, and I can do this because these are computed using the n minus 2 linear map.
Okay.
So that's the operation I can use to combine contributions from other people. If I'm Alice, and if I'm Bob, you come
So that's what you're publishing, right? So where do you get that information from before?
This is not what I'm publishing. This is
Okay.
the shared key. This is the output.
Oh, okay.
Yeah. So the two outputs need to be equal. The n outputs need to be equal. Yeah. So yeah, I can write the output polynomial as something like this. This is pairing stuff. So this one has degree less or equal to k minus 2, because that's the maximum level of linearity I have. And And then since I have my own secrets, I can really go wild. Any degree. So exponentiations are arbitrary. And when I write it this way, I'm not saying that Alice is computing it this way. I'm just saying that mathematically you can write it down like that. And that's important. Okay. So since this one has degree k minus 2, there is gonna be one monomial where not only I don't have Alice's variables, but Bob's variables are not gonna appear either, because there are n parties, n minus 2 is the degree here. Sorry, k parties, k minus 2 is the degree here. So there are at least 2 parties variables that are missing. So this implies there exists a monomial without Bob's variables. And I'm gonna focus on that because that's how I get to see that the overall polynomial has bounded degrees. So there's one polynomial without Bob's variables. Think about that. Cool. So I can write it down like that. So this is Alice's view. I can write it as monomial. This is not Alice, not Alice's, not Bob's variables, and then times a polynomial, and this is Alice's polynomial because it's Alice's view on Alice's variables. Okay. And you can do the same with Bob's. Yeah. Okay, I'll do the same with Bob's. So it's the same monomial, same thing, times poly B. I used colors there because I didn't want to deal with subscripts and okay. So now I'm gonna check what happens if I sample Alice's variables, essentially evaluating Alice's polynomial at Alice's variables. So yeah, so I want to show that these two polynomials are going to be correlated in a way that can be used by the attacker. So one thing I know is that if we take the two A and B and take the difference, that's going to be bound. Just a second. I evaluate first. I evaluated Alice's variables, so I'm getting an A. I'm going to write it at Alice's and B at Alice's. And I take the difference, so this minus B at Alice's. Actually, I want to evaluate at Bob's too, I think. So this thing here only has everybody's variables except for Alice's and Bob's, because I just evaluated. So it must be of degree less or equal than k minus 2. Yeah. And so remember now, these are the two views of Alice's and Bob's. And this is completely independent from all their variables. So this must be 0. Because if it wasn't, then these two would be different. Okay. Okay. And so that means that when I look at these two contributions for this monomial, they must be the same. So poly A, and this is evaluated at analysis. Must be equal to poly B. And these are both evaluated. So. So when I think of them as constants in their own, when they're evaluated at A equals A, lowercase a.
These are equal only modular groups, right?
Yes. Okay. So now one thing I want to do is I want to reverse what I just did in terms of Alice's variables. So lift up these two polynomials as polynomials in Alice's variables. And that's where the beauty of the approach is, I think, because essentially what I'm going to show you is that no matter how high the degree was in this polynomial, there is a lower degree representation that can be used by the adversary. So when I lift them in Alice's variables, what I get is that actually I need to change slide because I'm getting ahead. Yeah. So this degree here would be arbitrary, but this degree here would be bounded because Bob doesn't have any of the secrets that Alice already has. So this one has arbitrary degree, and this one is bounded. Yeah, so I'm writing, what I have in the slides is kind of like a smaller case than the general case, but you can think of this as being constant instead of just bounded degree. Okay, so let's say, okay, it's bounded, but you know, we know how bounded it is. It's k minus 2 minus something. And this is correlated to the degree we have here. So, in other words, if you sum this quantity with the degree that you have here, this is less than k minus 2. So then, well, I have a good representation of this polynomial in Alice's variables because I can just pick this. And that means that I can compute any of these coefficients as an adversary because I can use the k minus 2 linear map because I have this bound here. So, in other words, you iterate through all these monomials, and you know that there is a representation in in this case, Alice's variables that you can compute on your own. So do it for all monomials. And you're done, because, okay, I'll do it for the first, for the second one. So there is a representation of degree less or equal than k minus 2 that the adversary can use to reconstruct the shared key, just using the k minus 2 linear map. And this is the issue. There are too many monomials if k is not polylog. So I guess this is the failure, but since I said that it was bound, then it should be fine. Yeah, so I think that's pretty much it. This is the result we had. Like, now you see why the polylog restriction. You got a glimpse of the security proof. There's one thing I didn't say, which is on this. Yeah, there's an asterisk over there, like a poly star, because there is an interesting way that you can show that it's not that straightforward, but it's an extension of Schwarzschild. Yeah. Okay, so that's the result, and I think I want to spend maybe 2 minutes just saying why I got convinced that this was possible. And you know, Allison and Luke were talking to me in 2014, and I was like, oh yeah, sure. You just look at all the monomials and you can plot them somehow, and so on, like a triangle.
It was very convincing. You convinced me. So I tried to write it down.
Yeah. Yeah. So the way I thought about it was, you plot all the variables, all the monomials in a triangle where if, let's say this is P1, P2, P3, like from P2's perspective, you need to apply more linearity to go away from P2, P3 has the same, and so on and so forth. And I want to show that this thing in the middle is reachable only by two linear map in this case. So this would be x1, x2, x3. This would be something like x1 squared x2, and this is x1 squared x3, and this is x1 to the third. Like, these are all the monomials of degree 3 that you can represent with x1, x2, x3. So that was kind of the intuition I had at the beginning, and I was like, yeah, well, you make it a pyramid, and then you make it something bigger, and so on. But yeah, if you make it a pyramid, you get many more monomials and so on and so forth. So that's where this thing all falls. But it was very convincing, I thought. Like, you see the center of the thing. Yeah, but that's what we got. And I would be really, really happy to see the last restriction removed. So,
are you really convinced that it can?
I think that the proof has to be completely different if you want to do that.
Right, but not really the proof, but just, are you convinced that there doesn't exist some crazy way of taking advantage of a shared key polynomial that does use lower degree terms, but has so many terms that it's not an attack, and that somehow the legitimate parties have efficient representations of it that are higher degree but work for them, and that the attacker can't find an efficient representation of it, and therefore it actually is a key exchange scheme in the generic group of lesser degree. Are you really convinced that's not a thing? Because I started to believe that it would be a thing.
Yeah.
So at some point we split on this.
Yeah, I think.
How do you show that?
I don't know how to show.
So, what if we could come back like in 5 years or maybe 6?
Do we want to put some money on this?
Some Bitcoin.
Some Bitcoin. At whatever the future value of Bitcoin is in 5 years.
We need a stable coin.
I think going through this failure really made me change my mind about how possible that is. So I would say at this point maybe 60-40.
So it's pretty non-committal.
But if you're in team 60, go ahead. Also, if you're in team 40, sure. Cool. I don't have anything else. So.
Do you want to say anything about like the kinds of things we wanted to do after this? So we sort of thought of this as like a toy problem in a new domain of proving lower bounds from multilinear things. And this was supposed to be step one of like a 10-step plan. Do you want to
Oh
mention any of the other things that you thought about along these lines?
I think I was the one who was mostly focused on the geometric thing proof. But yeah, we were very ambitious. Like if you read the intro of this, you're gonna be really excited. Like we were thinking most of the cryptographic primitives that had this kind of symmetry among players and so on can be susceptible to this sort of attack or proof. What were some of them?
So for instance, in bilinear maps and lattices, we have functional encryption schemes like identity-based encryption, attribute-based encryption for formulas, and in lattices we have attribute-based encryption for circuits, and we don't have it from bilinear maps. It's sort of stuck at this formulas versus circuit layer. And we thought maybe we could prove something about the sort of polynomial representations in the exponent that would explain why, in a generic bilinear group, perhaps we can't have attribute-based encryption for circuits as opposed to formulas, which remains an open question. That's harder than this question. So much harder than this question potentially.
Yeah, I think along those lines we were really ambitious and wanted to make a parallel between LWE and bilinear maps, or try to disprove that there was a parallel and so on. So that pretty much what you said.
Yeah, which I think is sort of a separate question, but like there is this sort of intuition about the generic group as to that it really fences you in, and what you're doing is you're just forming these polynomials in the exponent, and you have the variables that you don't know, so you have very bounded degree in what you can do in them, and then the other variables you can use as arbitrary exponentiations. So we have a pretty good sense of like the shape of objects you can create. But when we put these sort of matching equality constraints on things, it sort of constrains the kind of objects. But I think what was really surprising to us about this work and what we hadn't anticipated was that it doesn't constrain the paths. So like we understand what different parties can make, but we don't really understand how they can make them. Like that there might be a way of writing something down in a certain form, and we do know that each individual party is sort of doing the generic group operations in their own exponentiations. But it suddenly became very hard to understand how those things link up when you look at them across different parties, that how to get to that same place while still, each following their own individual paths, which almost starts to feel like the isogeny stuff that you guys were sort of talking about yesterday. You have these different paths leading to the same thing. And that is not a trivial mathematical structure by any sense, and it lives in the polynomial world as well. So maybe there is eventually a polynomial-based crypto system out of the hardness of understanding these things. Probably not. But that's kind of where we got stuck, that we thought we had such a great sense of like the generic group should be easy to sort of study mathematically because we know how these polynomials are constructed. But what we don't know is how to do like Schwartz-Zippel kind of powerful theorems about those representations that match up with what a party can do efficiently, which is a very typical cryptographic kind of obstruction, that we understand the mathematical form in a general sense, but we don't understand efficient algorithms for getting to those forms.
Yeah, I remember that was maybe the last straw for us, because I I was adamant. I was thinking like, no, there must be an algorithm that you can use as an adversary to just, shave off whatever people created in their own way, because they have the secrets, but I don't have them. So. But I think that, you're right, like different ways of computing the same things, and is there an efficient way to map one against the other? Because in this case, each monomial, so we were looping through all the monomials, and for each one of them, yes, you can find an efficient reduction in terms of the degree, so that the adversary can use it. But then you're gonna fail because there are too many monomials. But is that a real limitation? Is it not? It's really unclear to me, like, what is the structure, like you said.
Yeah, because I think it's a lack of imagination for how could exponent secrets really be used.
Yeah.
We sort of had only been using them in positive schemes as that means you can create higher order terms. And there was this whole other gray zone that we didn't consider. Is it not that you can create individual terms of higher order, but is it that you can sort of short circuit the slow way of computing some long combination of things? And I think probably not,
Yeah.
but that seemed hard to understand.
So if I'm 60-40, are you 40-60?
Something like that, yeah.
Cool.
All right, any other questions?
So you briefly mentioned that you also have this restriction that the secrets need to be uniformly random.
Oh yeah.
I suppose this is somewhat easy to see, but I don't see it. So can you explain why that's relevant?
Yeah. So so if you sample exponents, or in this case, like secrets for the generic group handle, knowing that there is a correlation from an adversarial point of view can leak information. Like I can say, oh, well, you published these two random strings and I know that they're correlated, so I can use the bits in order to extract a different system and use that system instead of the, does it kind of make sense?
So a different way of accomplishing that restriction, so basically if you're trying to prove a generic group can't be used to do something, you have this kind of weird problem that like you just do the thing without using the group.
Yeah.
And so like one way that people get around that is by having an oracle that breaks everything else except the generic group. And I just kind of find that bulky and difficult to deal with, so I did like a much like harsher restriction, which is just that the only things you can do are produce random group elements. If you can produce sort of correlated group elements, you can just say, all right, I'll use a random element versus an identity element, and I can just encode bits. So I can just give you 20 elements, and you just read off which ones are the identity, and you just encoded however many bits, and then you could just do your other scheme. So if you're not going to deal with the overhead of an oracle, you have to use a pretty strong, and maybe you could relax it a little bit, but that's where it's coming from. It's avoiding somebody just doing a totally different scheme. All right, thank you for